Good afternoon or good morning wherever you are. Welcome to today's ACM SIGSOFT webinar. This webcast is part of ACM SIGSOFT's commitment to provide value to its current and future members. The ACM SIGSOFT webinar series features speakers from the future of software engineering track at the International Conference on Software Engineering, as well as select keynote speakers and distinguished paper authors. My name is Will Trace, Lockheed Martin Fellow Emeritus, and the most recent past chair of ACM SIGSOFT, the Special Interest Group on Software Engineering, and it's my pleasure to welcome you here today. Before we get started, I'd like to quickly mention a few housekeeping items for the first-timers. You've all had a chance to read the screen, so as you know, the slides will advance automatically throughout the event. And on the bottom panel of your screen, you'll see a number of widgets and resources. We'll like to remind you once again, at the end of the presentation, we'll have time for questions and answers. But please type your question into the Q&A box at any time and click on the Submit button. That'll help us get organized. Today's presentation is Teaching Future Software Developers by Václav Rajlich from Wayne State University. Professor Rajlich is the founder and permanent steering committee member of the International Conference on Program Comprehension and was the program chair, general chair, and steering committee chair of the International Conference on Software Maintenance. He's also a member of the editorial board of the Journal of Software Evolution and Process. Of most note is he is the author of Software Engineering, the Current Practice, a book which I happen to have written a review, and it appeared in the November 2013 issue of ACM SIGSOFT, Software Engineering Notes. This book provides a unique perspective on software engineering in that it explains software engineering not from a constructionist point of view, but from a change maintenance perspective, meaning most of the time you need to read and analyze programs rather than write them, though there is plenty of material in the book to support greenfield development. I thoroughly recommend the book. Václav, we look forward to your presentation here today.
Thank you, Will. I would like to start today with a Lament by Bjarne Stroustrup. He is the author of C++, which appeared in Communications of ACM a couple of years ago. And basically he complains that computer science graduates have no education or training in software development. And basically they learn software development on their own. For many, programming has become a strange combination of unprincipled hacking and invoking other people's libraries. I fully agree with his assessment of the current situation, and in this talk I would like to present a way how to perhaps remedy this situation. I believe that expectations of future employees and also of graduate schools is that computer science graduates should be able to work on software projects, and in other words, they should have software development skills. And so this talk will be geared towards answering the question how to meet that expectation. Contents of this webcast will be, first I will talk about the design of first software engineering course, then I will talk about code development basics, sometimes it's called craftsmanship, then I will talk about experience at Wayne State University, and finally summary and conclusions. Current curricula do not typically teach software development. current curricula assume that students will learn code development on their own. They may emphasize all kinds of stuff, sometimes very advanced, but that particular issue usually is not addressed, and there has been general unease with the way how software engineering has been taught. In order to explain the problem, this is the pyramid of skills, and which I would believe represents how software development should be taught. First, there is introductory programming, and I have absolutely no problem with the way how that is being taught. Then there is a technologies portfolio. Every single project has the whole portfolio of technologies which are necessary for that development, for that project to continue. And it's impossible to work on those projects without familiarity with this portfolio. Then there are those skills of code development, which is the main topic of this talk, and the way which I believe future software developers should be taught. And then there are other advanced topics which may be useful, which may be interesting, but they are kind of based on that knowledge of code development. Interactive programming is the first step towards developer skills. It's taught in programming courses. One of them is usually called data structures. And this course has the following objectives. It gives students confidence in their programming abilities. They should leave this course with the confidence that the computer is doing what they want it to do. Right? Another thing which they should resolve in that course is belonging. There's this issue of belonging into this group of co-developers, right? And some people may be turned off by this hacker culture, whatever. Right? These issues are the issues which should be resolved in introductory programming. And as far as the knowledge is concerned, people who finish those courses should have an ability to develop small programs which have 100 lines of code, maybe a couple hundred, right? And so this is introductory programming. After that, time comes to learn code development, and that requires those two steps as presented by that previous pyramid. First, to learn technologies for development, and then to learn the process of development. And that process and techniques of development should be taught on the level of students being able to do it, not just know about. If this is something what would be familiar to you, in terms of Bloom taxonomy, they should reach level 3 or higher. They should be able to apply that knowledge, not just to have passive knowledge of that. And that requires at least one course. This is something what many people do not realize, but to make these two additional steps, let me go back to that pyramid, right? To make these two steps beyond introductory programming requires at least one course. And so I will talk about those two steps first. So first one is technologies portfolio. Typical project has a core language in which the project is being developed. It has this IDE, again, which can be Visual Studio, Eclipse, and many more. There is usually a GUI in applications, database, there are testing tools like about the JUnit, there are modeling tools like UML, diagram, drawing tools. There is intra-team communication like Wiki. There is a version control. There's a whole bunch of technologies learn. Now assume that we have just one course to get that knowledge of code development. We cannot spend all that course just teaching technologies. There is simply too much stuff there. I actually have 7 different ways how the teaching can go wrong. I call them deadly sins. This is deadly sin number 1. Right? Too much time devoted to technologies. Right? And not enough time left for actual process of code development. Now, you have to understand that portfolio is a very specialized asset, and also technologies change at a fast pace. Right? There's always this technology fascination. Right? People love new technologies. They expect from them to solve the problems presented by old technologies. My advice is to teach only the necessary minimum, only to give the shortest possible shortcut through the technology, not to devote too much time. I know instructors who spend basically the whole course by teaching technologies. And now, when we talk about processes of code development, there are those processes which are applicable only to unusual situations, right? Like small programs, model programs is model structure. I believe that code development should be taught on realistic code with realistic size and complexity, and to make it more specific, I would say somewhere between 40 to 400,000 lines of code. Right? We are talking about education, right? Not about practical projects, but I believe that people get reasonable experience if they deal with programs of this size. There also should be realistic coverage of the domain. Right? If a program deals with a certain domain, it should realistically cover it, not to just have a couple of functions and ignore all the rest. And finally, there should be realistic quality. Current state of the art in terms of code quality, which is characterized by 1 to 3 faults per 1,000 lines of code. Moderate technical debt, that means code which is reasonable but not extra polished, not messed up, and so this is the code which I think people should be aiming at. Now, one of the old practices, old mainstream code development practice is waterfall. And here is the short overview of waterfall. Further, there is a collection of requirements, then there is design, then there is implementation based on the design, and finally transfer to the user and maintenance. Now, this code development practice is no longer mainstream, and one of the reasons why it's no longer mainstream is that there has been volatility of requirements, technologies, and knowledge. These 3 volatilities contribute to fast change in the environment in which the project happens, and based on that fast change, any design can be only temporary. After a while, it becomes obsolete because requirements change, technology change, knowledge changes, and then advantages of waterfall are no longer there. People have to react to that volatility. Another reason why waterfall is no longer a mainstream, why there has been this shift to a different way how to do things is that accumulated technical debt of waterfall is invisible to outside stakeholders. There are not only developers, but there are also managers, investors, bosses, users, all those other stakeholders, and they, in waterfall, have absolutely no idea what is the accumulated technical debt. They only get reports from the developers. Those reports, as we all know, can be somewhat rosy, somewhat optimistic. Right? There could be low quality requirements, suboptimal design, low quality early code, all kinds of things, and they come together at the worst moment possible, at the very end of the project, when the project is supposed to be delivered. In other words, too late. And so this is the reason why waterfall is no longer a mainstream in industry, and it's kind of, disappointing that up to this moment it is still a mainstream in academia. Right? This paradigm shift from waterfall to what I call evolutionary development happened about 10, 15 years ago. And the latest data say only 18% of projects are using waterfall. Right? And I believe that number is dropping, and maybe actually based on misunderstanding, my guess would be it's even lower than that. Right? And academia is still very heavily invested into waterfall. Right? There are textbooks, curricula, right, everything. And so this is something what I am trying to change. By the way, evolutionary development comes in different forms and different processes. I talked about it in earlier webcast in June. Right? Agile is perhaps the best known evolutionary software development. So it's a current mainstream. Right? It's based on adding new functionality to an existing software. In other words, software change. Right? It can be practiced on realistic code. You don't have to have people implementing 40,000 lines of code in one semester. Right? You can take already existing code of a realistic size and have them improve it, iterate on it, whatever, right? Make small change in a big code. Now, I advocate teaching evolutionary development as the current mainstream, adding one feature at a time. That's the so-called software change. Right? All stakeholders can check the result. Right? If there's a software which is not finished, but it has everything, including the current latest version of the code, they can just try it. Right? There is some of the technical debt becomes obvious to every single stakeholder. Right? Some of them not yet, but nevertheless, it's a much more open. They don't have to look into any big UML diagrams. They just see what's out there, and this is that's why it became current mainstream. Right? Just a little note: it's different from maintenance. Right? Maintenance, the kind of scale down process. Right? Only kind of keeping current software going. Evolution means adding new features. Right? So this is the current mainstream. And I would again formalize what I was talking about as a dead list in number 2. Right? Teach practices out of mainstream. Right? Preparing all these students to work on those 18% of software projects, or even less, I would say. Right? And completely ignoring those remaining 82% of the projects. Right? In old waterfall, realistic code is not attainable in the classroom. Right? There is no way how to give them experience with realistic code. Does not deal with volatility, accumulated technical debt. It's a minor practice today. It exists, but only in very special circumstances. And now, another problem which I see in teaching software development is addressing only top students. We all have, those top 10% of students in the class, and those are hackers. Right? They have their experience, and they don't hesitate to show it. Right? They sometimes play this intimidation game with other students, maybe even with the instructor. Right? If you teach something what they already know, they very brazenly yawn, right, in the class. Right? So this is a certain temptation. Right? I believe that we have to teach, those middle students. Right, students who can learn but do not know what is being taught, right, cannot figure it out on their own. This is the vast majority of the students. Right, we have a couple of those top students, and at the bottom we have a couple of those people who just can't cope with it. But all that middle, I believe, is our true audience, and so this is the people whom we should address. And so this leads me to that next dead listen, right? Skip code development basics, teach more advanced practices, right? Trying to impress those handful of advanced students who are sitting there, right? Middle students are not ready for them. They will not get them. Teaching will be superficial, right? They will not learn anything, right? So example of advanced practices is continuous integration. I just pulled out a couple of things. Managerial, right, teaching them how to manage project, before they know how to develop. Evolution of decade code, right, give them something nobody can understand and have them struggling with it. So those are advanced practices which do not belong into that first software engineering course. Now, another temptation is that first software engineering course as a survey course. Now, please remember that we have something like 60 years of software, 40 years of software engineering, huge amount of material. Right? I made a Google Scholar search, typed software engineering in, and got more than 1 million hits. Right? So there's a lot of stuff, right, in software engineering. And the question is what merits a slot in first software engineering course. Now, I argue that there may be some time in the course, maybe at the end, for survey topics, right? And I would argue that perhaps advanced practices, usability, promising new technologies, management practices, and professional ethics in particular, right, deserve some notion of time which is left in the course, right, after development skills are being taught. So this brings me to dead listen number 4. Survey occupies too much of the course, right? Graduates have this encyclopedic knowledge of, they know all these terms, but they do not have the skills, right? They are not really ready to work on the projects. And unfortunately, many textbooks are promoting this approach, right? Many of software engineering textbooks are basically encyclopedias of those 60 years of software, right? And so again, I see this is one of the ways how to go wrong, and have it here as a dead listen. Now, software engineering project. Right? If they want to learn the skills, they have to have a project. Right? It's an opportunity to practice those development skills which are being talked about in the lecture. And again, we have several ways how to go wrong. Dead listen number 5. So it's in a couple of places. Unrealistic expectations. You may have heard about death march projects. They were a big issue back in the 90s, right? So this is an academic version of death march project, right? Instructor gives them project which is practically impossible to do in a single semester, right? And holds them to it, right? Creates the hardest course in the curriculum, right? This is wrong introduction to the profession, right? This is a form of abuse, if you will. And sometimes they give them unfamiliar projects. Implement weather forecasting system, right? In one semester, right? You need PhD in weather modeling, right? It's a deadly sin, right? Unrealistic expectations, but I see it happening. Another is the wrong reaction to that. Basically, false remedy for that excessive demand, and basically asking them just to do superficial projects, to hollow it out, to strip the project of all software engineering practices, just to do some kind of make-believe, thing, which even word prototype would not be a good word for it, and something that works only for one set of data or whatever, some kind of fancy, GUI, but nothing else, right? So some engineering practices are missing, code quality is ignored. This is good for PR, right? To show it to the dean, look what kind of projects we are doing in our course, right? But it's not it, right? And finally, I have that last deadly sin, which is actually hitting those best students I talked about before. Students are graded based on the work of the others, right? They work in teams, and the whole team gets the same grade, and or there's some kind of poll where students are evaluating each other, right? And instructor then gives grades based on that, and this is extremely stressful for the best students who have to team up with students who are not as good, not as ambitious, who don't care about getting A in the course, right? And so this is deadly sin number 7. I have to admit here that years ago, I myself taught software engineering courses in this way. I apologize to my past students, but it's still practiced quite a bit. So after we talked about these problems, let's get positive now and see what should be taught. Right? I told you what should not be done, and now what should be done. So I think that basic task of code development is software change, right? Which adds or modifies the functionality of existing code. It is a basic task of all evolutionary development processes, whether it's agile, open source, inner source, all these processes, and there are quite a few of them by now, right? Basic task is software change. You have an existing software which is working, can be tested, can be used, and you add something to it. Of course, if we are teaching these students who know nothing except introductory programming, we have to give them a process how to make that change. Again, we cannot just throw them into the water and have them swim. Many of them would simply fail, right? So we have to give them a process. And so there is phased model of software change, where software change consists of the phases. Some of these phases are team interactions at the beginning and at the end. Right in the middle are phases where the students work individually. A couple of them are comprehension phases where they have to understand the code which they are going to modify, and then there is actually implementation phases in green, and they actually do the modifications, right? So this is the phased model of software change. Now, if you go through the changes, through the phases, first there is change initiation, where people analyze requirements for bug reports, select change requests. It usually requires a team effort. Then there are comprehension of old code. Typically, it's divided into 2 phases. First is concept location, feature location, which is just a fancy term for finding what needs to be changed in the code. It is a search through the code, find the location to be changed. It could be a class, it could be a method, it could be a line, it could be a bunch of classes, right? Simply the location. It is the key to the work in realistic software. If students work on realistic software, those 40 to 400K, they have to first find the location which needs to be changed. It's a key. Without it, they just cannot do anything. So there are certain techniques. There is good old technique grep, right, where people are basically searching for names, right? It's a very familiar technique. There are also others: dependency search, dynamic analysis. There's a whole bunch of techniques. But again, this is an introductory course, so only the basic techniques should be taught here. By the way, research of concept location is only about 15 years old, and this may be one of the reasons why this style of teaching software engineering is so unpopular, right? So people simply do not know these results, and so they don't know even how to start teaching software change, right? Then there's impact analysis, which determines the full extent of the change. Again, there are different techniques for that. Then there's refactoring, right? That old code may not be supportive of the change. In that case, it has to be prepared. It's called prefactoring, and the change may make a mess in the code. To clean up the mess is called postfactoring, right? So these two steps precede and succeed the change itself. There are numerous refactorings: function extraction, base class extraction, component class extraction, renaming. The website by Fowler on refactorings is about 80 different refactorings. Again, in this course, we are pressed for time. We need to teach only the most important ones. Then there is actualization, which in a naive view would be a change, right? People who don't do, or people who don't study this issue or who are not practitioners, they may think that software change is just actualization. It means incorporation of the new functionality, right? And again, there are a number of ways. There is polymorphism, where new functionality is implemented as a new derived class, right? There can be new component, right? This is a little bit more complicated. New composite APIs are geared towards new composite, right? You have API which gives you all kinds of functionalities, and you put them together into a new functionality, which are creating this new composite, right? Composite replacement. You may have old old component, you replace them by the new one, which does more than the old one. Then there is change propagation, where change propagates to other secondary places in the code, which have to be also updated. Then verification. Currently, the standard things of verification are testing, unit testing, functional testing, structural testing, or coverage. Right? They guarantee that code quality. There could be also inspections. So this is the verification. Now, in order to, then there's change conclusion, right? Commit updated code, resolve conflicts, if any, create new baseline. So this is the conclusion of the software change. Now, to make it more clear, this is an example of point of sale, which supports small store, supports only cash-only payment, and change request is add support for credit card payment. So this is a kind of, this is a UML class diagram for that small program, right? So first thing is a concept location. Where are we going to implement credit card payment? Well, there is a class payment there. And so that new functionality will go there, right? Here it's highlighted by red. Right? This is a small program. It's not difficult to find that class. But in those bigger programs, which have 100, 200, 1,000 classes, it can be a challenge, right? And so that's why we need to teach concept location as a topic. After that, we do impact analysis, right? It's not only this class will be impacted, but also class sale, where particular method of paying or purchase will have to be selected, or some code will have to be impacted. It's kind of obvious, right? Then there is prefactoring. Right? We already have a class payment. That class is dealing with all kinds of things which payment may entail. And why not to use these pieces also in payment by credit card? So we are going to extract base class here in blue from the class payment. And once we do it, right, everything that is common to all payments will be extracted into that class. And once we are done with it, we are going to add payment by cards, right? So this is actualization. So we are done with new functionality, but we have a mess here, right? We have these wrong names of the classes, abstract payment, and payment is actually cash payment, right? So we have to rename, we have to do postfactoring, which is in this case renaming. We rename class payment as cash and class abstract payment as payment, and then we are done with change. So this is basically what needs to be taught, right? You can imagine it's quite a bit of stuff, right? It's not like they can learn it on their own, or most of them cannot. This is just a reference to a tool, JRipples, which is a Eclipse plugin, which is doing impact analysis and change propagation in Java programs. Here two classes are impacted, class payment and class session, and class sale. And all interacting classes which interact with those impacted classes are marked as next. Developer is being prompted to inspect these next classes and see whether they also need to change, whether the change propagates to them also. So how does this look like at Wayne State University? This is our technologies portfolio. I have to make a little bit of disclaimer here. We inherit part of that portfolio from introductory courses. Right? Introductory courses are taught in C++ and Visual Studio, and basically I do not have a choice. To teach people different portfolio would be too much for this course. So we basically go along, use this in our software engineering course, but we have to teach all these other technologies, like for GUI, we teach Qt, build system, CMake, testing tools, unit testing, modeling, StarUML, version control client, Tortola, SVN, version control, SVN. And so we have to teach these other technologies before they start working on the project. This is the course schedule for 14 weeks course. In the left column are the lectures, and at the very beginning we teach a little bit of technologies, right? We have to tell them about version control in the lectures, right? So there is more in parallel lab. There's a lab once a week, meets once a week in parallel. So they spend first 3 weeks on technologies, right? So they learn a kind of shortcut through SVN, through GUI technologies, just basic minimum so that they can start working on the project. There's no time to give them full training of these technologies, only introduction, and basically we select projects based on that portfolio which they know, right? Main part of the course is the software change. Right? Those phases of software change are taught in weeks 3 to 10 in those yellow parts. Right? At the end, there's a little bit of time for overview, so other processes and professional ethics are overviewed at the end of the course. Now, in the lab, there are those assignments, and they are of about the same difficulty as assignments in other courses. They are basically asked to do 3 changes. The first one takes 2 weeks, second one takes 3 weeks, and the third one takes 4 weeks. There's, by the way, a long experience in this timing. Originally, we had the same time for each change, and they concluded incorrectly that the changes will be of the same difficulty, got into trouble with those more complicated changes. So we are sending clear message that the difficulty is increasing. So course projects run in parallel with the lecture. They work on open source, use based on students' technology portfolio, simple domain they already understand, like editors, graphic apps, file systems. I don't want to teach them domain in the course. So we also teach a survey in that last part, last 4 weeks of the lectures. So we teach them team practices of software evolution, like agile, directed, initial developments from scratch. Right? I did not completely give up on waterfall. We teach them a little bit in those 4 weeks left at the end. Final stages like servicing or maintenance, phase out, close down, the engineering. Just, on a very high level, we don't teach this as a skill to master, we just teach about it. Then there are other survey topics, right? Software engineering ethics is one of them. And although there is not much time left, I believe it's a very important topic, particularly with all these problems which are coming our way. And so all that data misdirection, misuse, and so I spent some time on software ethics. On software development ethics. In the questionnaire of past alumni, version control, working in a team, concept location were appreciated highest. Right? Most of them work as software developers. People from our course, I would say 80 to 90% end up as software developers. And the remaining ones end up doing something else. And they appreciate what they learned. They very often an email that the interview was based on the course. So finally, summary and conclusions. Future work, this is just one point in the time, right? The technology is changing, everything is changing. So we are planning to regularly update technology's portfolio. I presented what we currently use, right? It's not an obsolete portfolio, but it's not also the newest one, right? I would actually argue against going with the most recent pads that it pays to wait for the technology being kind of stable, familiar, right? So future work is, however, to update this portfolio as it kind of shifts. Another thing is to develop integrated phased model of software change tools. I told you about JRipples, which supports impact analysis and partially also concept location. But it would be nice to have tools which would basically guide students through the software change, where data from one tool seamlessly fit into the next tool. Right? Currently, they have to re-input those data. They have to sometimes change those data. So that basically hinders their education, and I speculate integrated tool would be also welcomed by practitioners. They also could help grading. Could build in a little bit of big brother into those tools, to tell us, how they actually did it. Might help with grading. I also think that there should be follow-up courses. Right? In academic world, these forces of inertia are just monumental. But this is my wish list, right? I am after we are going to get through this first software engineering course, which will teach them basic development skills. They should learn more, right? Like additional processes and roles. Role of the tester, role of the agile developer, which again has additional stuff, right? More about initial development, about design and code, more than we were able to tell in those couple of weeks at the end, right? Requirements engineering, new technologies which are exciting and new, right? Like cloud technologies, services-oriented architecture, end-user programming, which is also on drawing boards. All these things would deserve to have courses of their own, but they cannot be. It cannot be. People cannot expect that a single course of software engineering will teach it all, right? That single course of software engineering should basically step into that bridge, give people the basics, and give them code developer skills, so that we can face Bjarne Stroustrup and tell him, look, what you are complaining about is no longer true. Right? Our students know how to develop software. Right? So to change current situation where most valuable knowledge is self-taught, right? Currently students learning on their own, from their friends or from their own ideas, or they are being taught. Their future employers have to teach them that. Right? That, of course, is this chasm between classroom and practice. There are casualties of the chasm. There are students who get through the whole curriculum, maybe sometimes even with good grades, and only at the very end they find out that the basic thing which they hoped to learn is not even being taught. Right? And the parents who pay their tuition, right? So there are casualties of the way how things are being done, right? So again, the goal is to fill that chasm partially. And I don't claim that transition is seamless, and that's not my claim, but at least we should try to respect what is being expected. Right, and do something about it. Right, so do something about it. Right, and so this is the goal of how it should be taught. So this is my last slide. Will talked about this book. It's out there. You can it's available through Amazon and other places, and with that, I am ready for questions. Will?
Thank you, Professor Rajlich. We have a couple questions here, and once again, I encourage all the participants to submit your question to the Q&A box. They're coming in. Okay, so let's see. I'll take them in the order that they came. Is your Wayne State course available as a MOOC? Is it available online?
Yes, there's this website of mine which I can't actually display, and it has actually slides on the course, and it has also projects in the lab listed, so you can visit it. If you actually Google for my last name, you will get to it. My website eventually has all this material, and of course the book. These chapters of the book are basically
weeks
of the course, almost one-to-one. Right? So that will be another source.
Yes, the book is a good reference, and you have course material online that follows the chapters in the book. Second question, I find it easy to find lots of anecdotes why clean code is necessary, but very few empirical empirical research on the topic. Could you provide some solid research results on why clean code is necessary and its economic impact, if not emphasized?
Clean code is a kind of controversial terminology, right? If you remember, I talked about code with moderate technical depth. That's the code which I use in my courses, and which I believe is the realistic code of typical software projects in the industry, right? So I personally think that like in any other engineering field, you have to work with code which is within a certain range of quality. If the code is really decayed, it becomes a nightmare, and these techniques which I talked about no longer work. Right? But these techniques work in pretty wide range, right? And code does not have to be a model code. Actually, I believe it cannot. Right? If it's being developed by evolution, there has to be these new concepts which come into the code, which become part of the code. And if there are new concepts, they are not in the old code, so they have to be introduced, and sometimes by refactoring, right? So I would answer that code should be within certain range of quality, not necessarily perfect code, right? And I would see perfect code as being unrealistic, and I do not aim stuff which I'm doing at perfect code.
It is an academic exercise, and it is a goal to achieve, I'll just say, but nonetheless, they are students and they're learning, and sometimes you learn by your mistakes. So I'll leave it at that and move on to the next two questions, which I'm going to group and ask them back to back because they're related. How do you grade individual students and still teach, as in encourage teamwork? And the other question is, how do you address the sin of group grading in your class?
Well, we have quite a bit of documentation about both the individual and group behavior, right? We have these repositories, and commits to repositories are individual. And we also ask them to write individual reports on their change. How did they do it? What did they consider? What kind of help they got? This kind of stuff. So this is the individual part. Then there is the collective part. There are those conflicts, right? And actually, I have to admit here that with those late changes in the course, we actually create intentional conflicts. Right? In order to give them this team experience, they commit this conflicting code, and now they have to work out the solution. Right? They have to talk about it. They have to. One of them has to yield, right? And this is all monitored by the instructor. Right? So we have very individual idea of what that behavior was, and we are, I believe, able to give them a fair grade. One of the things which I experienced previously, creation of teams was one of those most stressful moments in the course. Right? Those people would be really stressed out who will be on that team. That's no longer the case, right? You can have in the team one of the best, one of the worst students in the course, and everything is fine, right? Because we exactly know who did what to whom, right? And so this allows this individual grading. And by the way, this is how it's done in the industry. On those teams, there's also quite a bit of teamwork, but every good manager knows who contributes how much, because everybody has their own individual visibility, right? It's a certain kind of wrong approach in academia to have these teams seen as a one unit and grade them, collectively. It is a deadly sin. That's the only thing which I can say.
Okay, let's. I'd like to move on to the next question here, and I'll just read it as written, and we can extrapolate as we need to exactly what the meat of this question is. But what would you like? What would be your view on coupling between the introduction to software engineering and systems development analysis courses? So systems, as in larger hardware software systems trade-off, and then just software engineering as you've outlined it as a change, viewed from a change perspective. Are we getting enough?
There are two parts to this question, right? One is what is the current state of the art? Currently, we are struggling just with software development, right? But these system development things have very many things in common, and complex systems. Although hardware is not as changeable as software, complex hardware is becoming more and more complex and may require also more software-like techniques. Once the hardware is going to be done in evolutionary way, and I believe that we are heading in that way, then these techniques will be applicable to hardware also.
Okay, our last question. How would the evolutionary development model be best implemented in a requirement-driven industry such as government contracts?
Well, I believe that it is the only workable model, right? We've seen actually quite recently this failure of the health website, which I understand was done by Waterfall. And even if there is this book of requirements, they are volatile, they change, right? And they understanding grows, right? Original understanding is different than understanding at the end. So I think that the only way how to do it is to pick a subset and do the first version, then another subset, next version, and this is basically evolutionary development, right? And
very good. Well, I'm afraid we've run out of time today, and I'd like to thank Professor Rajlich again for his informative presentation and insightful answers to the many questions. A special thanks to each of you for taking the time to attend and participate today. This webinar was recorded and will be available online in a few days at www.sigsoft.org/webinars.html. You can find announcements on upcoming SIGSOFT webinars and other ACM activities at learning.acm.org and on the SIGSOFT website. I'd like to point out what's not on this chart, that tomorrow Bertrand Myers is giving a talk on design by contract, a guiding principle for software quality. And the next SIGSOFT webinar is probabilistic programming, algorithms, applications, and synthesis at the end of the month. That said, this is Will Trace saying goodbye for now. Thanks again for joining us, and hope you will join us again in the future.